Today we are talking about Faraday's Law of magnetic induction. Now, magnetic induction runs a lot of things. It relates electricity or electric fields and magnetic fields. This right here is a wireless charger. It consists of a loop of cable that current runs through that then induces a magnetic field around it, which is then able to interact with the similar loop of cable in your phone, which then creates electricity, which then is able to charge your phone. So essentially what we're saying is magnets equal electricity. At least sort of. It's not necessarily the magnets themselves so much as changes in magnetic fields, which creates a current, and vice versa. Changes in current create magnetic fields. Here's an example. When we talked about force and acceleration and speed and velocity in Newtonian physics, let's talk about an object with a constant velocity, with no friction. What's the force? There is no force. It's just moving at a constant velocity. That velocity could be 0, that velocity could be 100 miles an hour, it doesn't matter. There is no force, there is no acceleration. However, if suddenly we take friction into account, what we get is a need for a constant acceleration to oppose that friction. Friction opposes motion, so if the car is moving forward, friction pushes in the opposite direction. And in order to overcome that friction and maintain a constant velocity, we must accelerate so that that force going forward is equal to the force of friction pushing us backward. Remember, friction opposes motion. Opposes is the key word here. So this is Faraday's law. We have E equals negative N over the delta phi over delta T. E is the voltage or the EMF. N is the number of loops in your coil. Phi is the magnetic flux or the change in magnetic flux, and delta T is the change in time. Again, we want to really emphasize the change here. Things are changing and that creates the voltage. This is the equation for phi. Phi is equal to BA cosine theta, where B is the strength of the magnetic field. It's in how many teslas the magnetic field is. A is the area of the loop. And theta is a little weird. Theta is the angle between the magnetic field and a line orthogonal to the direction of flow. We don't need to worry about that too much, because we're just going to assume theta at the extreme, so either at 0 degrees or 90 degrees, parallel or perpendicular. If the flow is parallel to the magnetic field, then there's no magnetic field created. There's no electricity created. However, if the flow is perpendicular to it, it creates a magnetic field or a current. The biggest thing, again, we want to emphasize here is change. Delta is change. Change creates things. A change in force or a change in acceleration causes a change in velocity, whereas with a constant velocity there is no change. Forces come from change. So here we're going to observe an example. We're writing out our equation here. We have phi 2 minus phi 1 over delta t times negative n. We'll go ahead and replace those two phi's with those equivalent equations. And here's this loop. So in this loop, we have a loop running through a magnetic field. These x's mean that the magnetic field points towards the board. It's like an arrow shooting into the board. So what we're going to do is we're going to use our right-hand rule to determine the direction of flow. We cup our hand, and that tells us which way the magnetic field corresponds to which direction of flow. In this case, with our hand pointed downwards, we see that the flow that would go into the board and come around the outside of the coil, and thus the magnetic field, thus the current must be heading downwards towards our thumb. So if we increase magnetic field, our voltage also increases. If we increase the number of loops, our voltage increases. If we increase time, our voltage decreases, because the larger time means we're dividing it by that. Larger change in time means less overall voltage. We'll assume that cosine either results in 0 or 1, or rather an angle of 0 or 90 degrees. If cosine results in 0, then there is no magnetic flux created. Here's another example with 2 loops. We'll say the current is flowing this way in this one. Using our right-hand rule, we can see that the magnetic field comes out of the loop. So these circles are like an arrowhead and represent the field coming out. And then they pass into this other coil without any current going through it, and so that's just the field going through on the other side, going into the board. And using our same right-hand rule, we can see that the direction of flow must be in the clockwise direction. And again, I'd like to emphasize that this only happens when there's a change in current. So if current increases in the left coil, it will induce a stronger clockwise current in the right coil, because the coil on the right-hand side will try to create a magnetic field that opposes that on the left. So if the current on the left becomes weaker, the coil on the right will try and create one to oppose that weaker change, meaning it flips direction. Here's another example. Someone has a hand and they have a wedding ring on. Congratulations. No, seriously. So someone has a wedding ring on in a magnetic field flowing this way. They move their hand from outside of the magnetic field into the magnetic field. So here's our equation, and let's look at how things change. So if we plug in our numbers, we have one loop because it's just a ring. So we have our 2 BA cosine thetas over delta t. We can eliminate the second BA cosine theta because it was outside the magnetic field. B is 0, so we don't even have to consider it. So we'll go ahead and rewrite our equation. B times the cross-sectional area of the ring, so pi r squared, times cosine of 0, because we're in perpendicular to the electric field. Thus, if we solve that equation, we will then figure out what our actual voltage is. If you guys want to learn more, follow me. My username is @JustinPallo.